We come now to a new theorem, and this is the extreme value theorem. You may have discovered that calculus tends to like theorems that end with the words value theorem. We've already seen in chapter 2 the intermediate value theorem, the IVT. We come now to the extreme value theorem, the EVT, and a little bit later in this chapter we're going to have one more called the mean value theorem, which is the MVT. But here is the extreme value theorem, and what it says is suppose that f is continuous, that's an important condition, on a closed and bounded interval, and that's the other important condition. We'll see why in a minute. And when I say closed and bounded, all I mean is that the interval ends with, on both ends, with the square brackets to include its endpoints, and it is in fact a finite length interval. It's not an interval that goes on forever. Then the theorem states that in this case, f attains both an absolute minimum and an absolute maximum on the interval AB. And you can see that here, just to put just an example function that is continuous on the interval AB. And what we can see is that f does have a maximum. That's clearly the highest value that f attains on the interval, and the lowest value that f attains is down here. That's the absolute minimum. So it's sort of easy to see that if the function is in fact an unbroken ribbon and it includes its endpoints, then it's going to have to attain some maximum value and some minimum value. Now you might say to yourself, well, doesn't every function have to have a maximum value and a minimum value? But the answer to that is no. And I want to show you why these two conditions are actually important. So let's take a look at here. Let's look at why continuous, enclosed, and bounded matter as conditions. So on the left, you see a function where I've drawn it so it's not continuous on the interval AB. It's defined on the entire interval AB. Even at this point here, it's broken, but it is defined at that point. So this function does not attain a maximum. And as you can see, what happens here is you might look at this and say, well, wait, isn't that the maximum? But it's actually not, because you see by the open dot, the function never actually gets up to that point. Let's just put in a value here. Let's just call this L. And you see the function never actually gets all the way up to L. It keeps getting closer and closer and closer and closer to L, but as indicated by that dot, it stops right there and then jumps down here. It never gets up to L. So the thing about L is not a value actually attained by the function. Go back to here, it says suppose that f is continuous then and closed and bounded, then f attains both an absolute minimum and absolute maximum. So L sort of in a very real sense is the highest value of the function, except that it never quite gets there. The term for L, we're not really covering this in this class, but we'd say L is a least upper bound, or the term we use in Latin is supremum. You don't have to know those terms. I just thought some of you might find it interesting. So L is an upper bound, and in fact, it's the smallest upper bound of the function f, but it's not actually a value attained by it. The fact that it's possible for this function never to attain any maximum is made possible by the fact that the function is broken. It's not continuous. On the right, we have the other condition, an example of why the other condition matters. If the interval is not closed, and this interval here is not closed because in order to be closed it has to include both of its endpoints, not just one of them. If the interval is not closed, then look what can happen. This function, as we approach 0 from the positive side, it just goes all the way up to infinity. It never achieves any maximum value because any number that I can put in that I can say is the maximum value, I can always get a little bit closer to 0 and get to an even higher value. That's what it means to say that this function is approaching infinity as it approaches 0 from the positive side. And then on the bottom, I just put in another example of this. Here we have y equals x squared, and we see that if I limit its domain to the open interval -1, 1, then for the same reason as in this example here, we can see that 1 might be is the upper bound on the function, but x squared never attains the value 1 on the open interval -1, 1. So by allowing the interval either to be open or allowing the function to be not continuous, we leave open the possibility that the function never actually attains a maximum or a minimum or fails to attain both of them. So that's the significance of this theorem. It says that as long as we limit the function to being A, continuous, and B, on a closed and bounded interval, then f is guaranteed to attain both an absolute maximum and an absolute minimum on AB.